Okay, this video is the fifth one in our Chapter 4 videos, and basically what I'm going to talk about in this one is grin fiber modes and grin fibers, and to try to just give you a summary of grin fibers before we get on to the topic of dispersion. Okay, and let me just summarize the equations for a grin fiber here. You recall that we have an index profile typically parabolic, but as I'll show you, it may not be necessarily. If we have a core index of n1 and a cladding index of n2 outside of a certain radius of the core, then we're going to have the cladding index. So, and then in the core, remember A is the core radius, we're going to have some sort of an index profile that may look like that. And we can write an equation for this, n as a function of r, which looks like this. For r less than or equal to a, we'll have n1 square root of 1 minus 2 r over a to the alpha times delta. And this is for r less than or equal to a. Hope you can still read that. It looks like you can. And for r greater than a, we're going to have 1 minus 2 delta underneath the radical sign here. And this is going to equal n2 for r greater than a. Okay, so this, you can plug in the definition of delta and verify that these equations work out. You can plot that in Excel, for example, and see that it all works out. Alpha characterizes the index profile. Variable. And if alpha is equal to 2, we get a parabolic. And I think that's the most common. But this equation gives us a variable alpha, for example. We can vary the alpha and change the index profile. As alpha gets larger than 2, it sort of flattens out the top of this index profile. And if alpha goes less than 2, it sort of turns it into a sharper point at r equals 0. Okay, so there's a couple of different equations that we can write down for the grin fibers, and we're not really going to make a mode plot, so I'm going to say no mode plot given. You may notice that that's missing in the book, but we do have n2 less than or equal to n effective less than or equal to n1, just as for step index fibers. And we can write that the n effective is equal to n1 minus p plus q plus 1 square root of 2 delta over k naught a, where a is the core radius, k naught is the propagation number in the vacuum, delta is the standard delta, and p and q characterize the modes. They're integers or natural numbers. These characterize the modes. Yeah, a lot of, in the same way that we had these two subscripts on the modes for the various modes in the step index fiber. We had the HE11, TE01, TM01, TM02. So there's two numbers there that are characterizing these things. And those two numbers are more or less the numbers which sort of characterize the symmetries of these modes. You'll see that these diagrams are labeled with L and M. Here's the L0, M1, L1 and M1, L2, M1. So basically, the P and the Q in our step index fibers are characterizing a whole bunch of different modes with different symmetries based on the P and the Q. Okay, and so the lowest order mode, is more or less Gaussian, and it has P equals Q equals 0. Okay. The number of modes, remember for the step index fiber we had an equation which gave us the approximate number of modes. We can do the same thing here. N is approximately equal to V squared over 4. Aha! This helps us to understand why GRIN fibers are used for multi-mode applications. If we go back to the equation for the number of modes for a step index multi-mode fiber, it's V squared over 2. Here we've got V squared over 4. And so this is roughly half the number of modes as a step index fiber with the same V value. And that's one of the reasons that GRIN fibers are used for multi-mode fibers, because they have fewer modes, and therefore they are going, and we'll see the equations in the next couple of videos, they have much lower pulse distortion, okay, or less delta tau. Finally, we can write down an equation for the condition for single mode behavior. For step index we had a maximum V value. It's sort of a different type of equation, but it's again, for step index we had that V was less than 2.4, and V was very much like our D over lambda, and it has A over lambda. For GRINs we characterize it in terms of A over lambda again, condition SM condition. So single mode behavior condition is that A over lambda is less than 1.4 all over pi times the square root of N1 minus N2. So this is empirical, I think, an approximate. Okay, but it is, at least in terms of a ratio A over lambda, which is familiar to us from our slab index plots, and it's also familiar as something, a term which is more or less in the normalized frequency, which is the horizontal axis here. Okay, so that's the approximate equation for single mode condition. I think that's it. I won't take the time to do an example problem, and in the next video we'll start talking about pulse distortion and information rates. Thanks.